Hello. This class we will continue with our arithmetic instructions. We have few more instructions belongs to arithmetic group, and we will completely cover logical instructions. Okay. So under the arithmetic instructions, we have increment instruction. Its opcode is INC, and the instruction supports the following operands. INCA meaning is it increments the content of accumulator. Accumulator will be increased by A. For example, INCA, if A is 0 0 0 0 0 0 1 0, then after executing INCA, it will be just perform plus 1. Then content will be 0 0 0 0 0 0 1 1, means 0 1 will increase to 0 2. Every increment it will increase the content of accumulator by 1. Similarly for other registers, INC Rn, example INC R0 to R7 we can use. Okay, every time content of the specified register will be increased by 1. Then INC R0 direct addressing mode also we can use here. Example INC 20H, content of the memory pointed by the 20 will be increased by 1. Then INC R and INC at Rn, example INC at R0. If R0 is equal to 47H, then INC at R0, the content of the memory from 47. Suppose it was 05, after executing the instruction, the 47th location will increase to 0. What was it? 05 become 06. Now INC DPTR, data pointer will increase to 1. DPTR is a 16-bit register, so 16-bit register DPTR. So we have DPH and DP low. Okay, on executing INC DPTR, the lower order bits will be, or the content entire 16 bits will be increased by 1. That is what our increment instruction. Next is decrement instruction, and the opcode is DEC. So it supports with the DECA, same like what we discussed with the INC. DEC will decrease the count by 1. Okay, one point to remember here is if content is f of, for example, A is equal to, content of A was f of, on executing DECA it will roll over to 0. That means on decreasing from f of by 1, accumulator will become 0 0. Similarly INCA will increase to 0 1. INC if yeah, that's all. INC will increase to 0 1 only. DECRN, similarly DEC from R0 to R7 is possible. DEC address, DEC as we discussed with INC instruction, DEC 20H will decrease the content of that memory 20 by 1. Then DEC at R0 or R1, okay, in direct addressing mode. Next, multiplication instruction. So addition, subtraction, increment, decrement. Next type of arithmetic instruction supported within our microcontroller is multiplication. So 8051 supports byte by byte multiplication only. The byte are assumed to be unsigned data. So signed and positive negative way of representing is not possible within the microcontroller. Whatever be the number, it will treat it as positive number, and the result will be available like this. Lower order bytes of the product will be within the accumulator, and the higher order bytes of the product will be within the B register. So both A and B are two registers that supports arithmetic operations within 8051. Okay, so mul AB is the opcode. So instruction format is mul space A comma B. It means A into B. This instruction will not support any other register. For example, mul R1 R2 is not support within our microcontroller. So it should be within A and B register. Both operand or multiplier and multiplicand should be within the A and B register. So result will be 16-bit register, higher order in B and lower order in A. So for example, this is an example program. Move A comma 25H. For extracting or executing this instruction, content of accumulator will be 25 here, and on executing move B comma hash 65H, immediate data 65 will be copied to B register. So content of B will be 65. It will perform 25 into 65 while executing mul EAB. Remember, the multiplications will be in hexadecimal system. Hexadecimal system, not in decimal. It won't multiply 5 into 5 is 25, 2 5 is 10, 10 into 2 1 12. Then like that, the result will be in what you call hexadecimal number system. And multiply on multiplications, we will get the result like B is equal to, or our answer product will be E99 equivalent to 625 into 65. It is E99. So E99 will be holding within the register B is equal to 05. B is equal to 0E. B is equal to 0E. This content, and accumulator will be 99, so that the programmer should inspect both B and the A register to get the product. Next is division what you say equation. Instruction opcode is DIV. So instruction is in the form DAB. Also it involves within accumulator and B register only. No other registers are supported for division operation in 8051. So supports byte over byte division only. So it performs A by B only. B by A is not possible. For example, div BA is not supporting in our microcontroller. Now, so here it is not mul AB, it is div AB. So example also given here. Move A comma 95. On executing this instruction, A will be 95, and move B comma 10. B will be 10. Remember, this B is 16, equivalent to 16 in decimal system. 10 is in hexadecimal system. On executing div EAB, 95 divided by 10 will be executed. Whatever if it is in the hexadecimal or decimal system, it follows same division as in the decimal system. So 9 times then 90, then remainder is 5. So we will get A is equal to 09. So accumulator quotient will be 09, and the remainder B will be within the B register. So our answer quotient is in accumulator register, and the remainder will be in the B register after the division instruction. Byte by byte it perform A by B, quotient in A register, and remainder in B register. So while executing the instruction, carry flag is always 0. Carry flag is always 0. So carry flag will be modified after the division instruction. If B is not equal to 0, over flag is equal to 0. So sometimes if the division instruction completes with the remainder 0, then if you divide again, B is not it indicates an error value. If as we know, something by 0 is not defined, so that not defined will be indicated by within the overflow flag. So the programmer should check the overflow flag whether it is 1 or 0. If it is 1, it indicates the division has not performed. It results with an error value. If over flag is a 0 value, or if there is a remainder, over flag become 0. Okay, if the remainder is 0, it will indicate the remainder is 0. Then if over flag is 0, you should not indicate, you should not go for further division. Okay, that is what our division instruction. Next, logical instruction. So we have completed within with our arithmetic instructions. We covered addition instruction, subtraction instruction, increment, decrement, multiplication, and division instruction. Next is logical instruction. So logical operations we studied within the LCT subject. Logical operations supported within our microcontroller. So first one is ANL. ANL, destination comma source. Destination is equal to destination and source. What does it mean? It perform logical and operations between the content of destination and source register, and the destination will be modified according to what the operations between the destination and the source. Okay, what AND operation between destination and the source. Instruction will perform a logic AND on the two operands and place the results in the destination. Destination is normally the accumulator. Source operand can be, so that first this point, this register must be an accumulator register. Most of the instructions are supporting for destination as accumulator, and the source can be a register, any of the register from R0 to R7. In memory, you can put any memory locations like this, or an immediate data like hash 27H. Okay, so that are sources. So sources can be any of the two, but the destination should be accumulator for performing. And remember, the operations will be bit by bit. Example, show the results of the following. Move A comma 35H. What the instruction is doing while executing move A comma 35. So let us see, while executing the instruction, A is equal to 35. How is 35 represented within the microcontroller? It is 3 by 0 0 1 1, 5 divided by 0 1 0 1. So D0 will be 1 and followed D7 will be 0 within the accumulator on first instruction. Now the command is saying ANLA. So first destination is given as accumulator and source is given immediate 0F. So the destination or a source is given. Let us write it as content of source is equal to 0F. 0 means 0 0 0 0. F means 1 1 1 1. Okay. So while executing this instruction ANL A comma 0F, what A1 dot 1. So by the way, what is AND operation? AND operations we have the following order: 0 0 0 1 1 0 then 1 1. So A B Y might have learned within the logic circuit. 0 dot 0 is 0, 0 dot 1 is 1, 1 dot 0 is 0 dot 1 is 0, 1 dot 0 is 0, 1 dot 1 is 1. So output will be 1 if both inputs are 1. In other cases, if any of the input is 0, output will be 0. So 1 dot 1 is 1, 0 dot 1 is 0, 1 dot 1 is 1, 1 dot 0 is 0. Then 0 dot 1 is 0, 0 dot 1 0, 0 dot 0 0, 0 dot 0 0. So after executing the instruction, our accumulator will be A is equal to 0 0 0 0 0 1 0 1, which is nothing but this is 0 and this is 5. So before the instruction, accumulator was 35. After the instruction, accumulator is equal to 0 5. So lower order bytes is not affected, higher order bytes is 0 after the instruction. That means these instructions we can use to mask, to clear a particular nibble within the accumulator. If you AND with the 0F, if you AND with the 0F, what will happen? Higher order bytes will be, wherever you have the 0, higher order bytes will be masked. Means we can take the lower order bytes from that. Then if you AND with the F0, what will happen? F, higher order bytes will retain, but lower order bytes will be masked. So lower F0 make lower bytes will be masked. On executing with the ANL A comma F0, lower order bytes will be masked. ANL A comma 0F, higher order bytes will be masked. Okay, that is one of the use of AND instruction, ANL instruction within the 8051, not only with all microcontrollers and operation. Next is ORL. It is very clear. ORL, it will perform logical OR operation. So instruction format is ORL destination comma source destination will be modified. So as within the ANL instruction, ORL also performs bit by bit logical OR operation, and the result will be updated within the destination. As in the in the ANL instruction, destination must be always accumulator, and the source can be a register from R0 to R7 in memory, say 20H, or an immediate data hash 20H. Okay, so that are the possible sources of content, sources of value for the ORL instruction. So this also will let us see what will happen after instructing, after executing an OR operation. So what is OR operation? OR operation, suppose we have two inputs, say A and B, and we have the output. Okay, so possibilities are 0 0, 0 1, 1 0, then 1 1. So what will happen? So basic logical operation, 0.0 is 0, 0 plus 0, logical operation is plus, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 1. So output will be 0 only when both inputs are 0. If at least one input is 1, output will be 1. Okay. Now on executing this instruction, our accumulator will be A is equal to 0 4. How 0 4? 0 0 0 0. Then 4 is 0 1 0 0. ORL A comma 68H. So our source is given an immediate data which is 68. 68, how it will be? 0 1 1 0. Then 8 is 1 0 0 0. On executing the command ORL A comma 68, it will perform bit by bit OR operation. So 0 plus 0 0, 0 plus 0 is 0, 0 plus 1 1, 1 plus 0 1, 0 or 0 is 0, 1 or 0 is 1, 1 or 0 is 1, 0 or 0 is 0. Okay, so what will happen? Accumulator and source data content bit by bit OR operations will be performed, and the accumulator will be, or the destination will be modified according to the result of OR operation. That is what the application of how OR instruction, ORL instruction within our microcontroller 8051. Now third type of OR or logical operation supported within our microcontroller is XRL. XRL is nothing but exclusive OR operation. Okay, before that, what is an application of an ORL? I forgot to tell you or discuss application of XRL instruction. Okay, check here. In this instruction, what you say? If the content of any bit is 0, okay, if you OR the content with any other register with the content of any other register whose a particular bit is 1. For example, in 68 D3 is 1. 68 D3 is 1, while for within the accumulator D3 is 0. After executing ORL A, 1.0 become 1. So we can ensure that after executing this ORL operation with a data whose accumulator or source bit is 0, corresponding destination bit is 0 and the corresponding source bit is 1, the result or destination that corresponding bit will set to 1. For example, if you want to set the LSB bit, you can OR it with a data, what do you say, 0, 1. What will happen? For example, in the same instruction, A is equal to 0, 0, 0, 0, 0, 1, 0, 0. If you perform ORL A comma hash 0, 1. So 0, 1 is 0, 0, 0, 0, 0, 1. While performing the OR operation, 1 dot 0 is 1 or 0 is 1, 0, then 1, 0, 0, 0, 0, 0. So before D0 bit was 0, while executing it become 1. So if you want to set a particular bit only, if you want to set a particular want to ensure that a particular bit only to 0, you can perform the OR operation with what you will say, corresponding bit is equal to 1 in the source register. So that is one of the application of ORL instruction. Now XRL perform exclusive OR operation within the accumulator or the destination and the source bit by bit, and the destination will be modified according to the exclusive OR operation. Source destination is always the accumulator, and source, as in the previous X cases, source can be register R0 to R7 within the memory, say direct 27H, or an immediate data 27H. So these are the instruction for format of XRL instruction. Now how it works? So XRL instruction, how it works? So let us see what is the truth table of exclusive OR gate. So exclusive OR gate, say we have the two inputs, for example, say X and Y is the input, then X XOR Y, or A and B, whatever. So possibilities are 0, 0, 0, 1, 1, 0, 1, 1. 0 XOR 0 is 0, 0 XOR 1 is 1, 1 XOR 0 is 1, 1 XOR 1 is 0. So this is the output for the different cases. Look at the output. Output is 1 whenever both inputs are different. Outputs are 0 whenever both inputs are same. That is the logic. Whenever both inputs are different, whenever the inputs are different, exclusive OR become 1. When same input, for same input, exclusive OR is 0. So okay, let us take one example. A is equal to 54. So while executing the instruction, A will be 54. How is 54? 54 is 0, 1, 0, 1. Then 4 is 0, 1, 0, 0. Next, XRL A comma 78. So our source is equal to immediate data 78. How 78? 0, 1, 1, 1. Then 8 is 1, 0, 0, 0. Okay, we will perform bit by bit exclusive OR operation. 0 XOR 0 is 0, 0 XOR 0 is 0, 0 XOR 1, different input, output is 1, 1, 0, different input, output is 1, 1, 1, same input, output is 0, different input, output is 1, same input, output is 0, same input, output is 0. So while executing XRL A comma 78, our result is 0, 0, 1, 0, 1, 1, 0, 0. So what happened in while executing the instruction? So okay, so if you perform XRL again, let us see. So we will perform XRL A comma 78. XRL 0, 0. What will say? We will see the application in detail once in the next slide. So if you carefully examine the result within the accumulator, it was 54. 0 becomes 0, 0, 1, 1. Can be used to So application, anyway, I will tell you what is the applications. We can use it to toggle certain bits of the operand, to toggle certain bits of operands, meaning if you continuously exclusive over the content of a register, it will toggle 0 become 1, 1 become, for the next time 1 become 0. So that is what frequently it will toggle a particular bit. So for example, if you exclusive over the content of with 78 again, so it become here 1, so 1 becomes 0. Then again 78, for example this bit exclusive or we will take the bit alone, then toggle with the 78, when forget other bits, next time it become 0 again. If you toggle with the 78, then 0.1 become 1. So every time every time after executing the instruction, the bits corresponding a particular bits we can toggle. 0 can change to 1, 1 can change to 0. That is one of the application of exclusive OR instruction. Another instruction is, let us see another instruction. XRL instructions can be used to clear the content of a register by XORing with itself. So one of the second application of exclusive OR instruction is we can use it to clear the content of a register, to clear the content of a register, particularly accumulator, by XOR with itself. Let us see how it is. For example, we have an instruction move a comma hash 45h. Okay, then we will perform XRL a comma a. So what is 45? 45 content is 0100, 5 is 0101. Okay, then XRL a, it will perform exclusive OR with a itself. So source also 0101. Okay, let us see what will happen. 1.1 XOR 1 is 0, same input 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 0. Okay, that is what our exclusive OR operation with itself, or XRL with a makes, XRL a comma a makes the content of accumulator as 0, 0. So we can use this instruction to clear the content of accumulator. Same what we implemented with the CLR a, it will make. So XRL a comma a and CLR a both are having the same result on executing a with the XRL. So XRL we can use, one of the application of XRL instruction is we can use to have the same result. Okay, now to another application, this is second application. First application to toggle a particular, second application I will write here, to toggle a particular bit of a register. Then the third application is, to compare a register, to compare a register with the accumulator. We can perform the comparison. For example, suppose we have our register R0 content is say 47H and accumulator is some another value, for example 27. Then we perform XRL a comma R0. What will happen here? For a is equal to 0010, 7 is 0111, then 47 is our R0, this is a 27, R0 value is 47, 0100, then again 7, 0111. Okay, while performing the exclusive OR operation, same input 0, same input 0, 0, 0, same input 0, different input 1, different input 1, different input 0. So this is the content of the accumulator after performing XRL A. Now suppose our R0 is same, accumulator is also 47. So suppose A is, this is case 1, then case 2, accumulator is say 47. So A is equal to 0 1 0 0, 0 1 1 1, and R0 also 0 1 0 0, 0 1 1 1. Okay, while performing the instruction XRL A comma A, same input 0, same input 0, again 0 0, same input 0, same input 0, same input 0, same input 0. See, look at the difference here. If both are 0, here this is the case, R0 is equal to 47, accumulator also 47. This is the case here. And here is R0 is equal to 47, A equal to 27. This is the case. So if both content, accumulator and register, are same value, while executing the XRL A, accumulator result will be 0, otherwise a non-zero. So how we can compare two registers? We can perform XRL A comma whatever be the register you need to specify here. Then jump on 0 or jump on non-zero, and so we are going to discuss this in later. Jump on 0 or jump on non-zero commands we can use to perform what you say, if they are equal, perform some another duty, otherwise perform another set of duties. So that is one of the third application of XRL instruction. Next, PLA, complement the register A. Very clear complement. It just invert the content of the accumulator. Okay. So for example, move A comma 55. So while executing the instruction, A will be 0 1 0 1, then 55 0 1 0 1. Then CPLA make bit by bit 1 0 become 1, 1 become 0, then 1 0, 1 0 1 0. That is the content of accumulator, every bit within the accumulator. So A 55 we can change to AA by making every bits to its complement. Then if you want, if the question is find the 2's complement, how we can find the 2's complement? Perform 2's complement by adding 0 1 to its accumulator. So if you have A is equal to 55, question is they're asking you to find the 2's complement. So instruction to do is CPLA, next instructions must be ADD A comma hash 0 1 H. That is the command. ADD A comma this will make accumulator is equal to 2's complement of our accumulator register. So the one of the application of CPL. Next is clear A, very clear. Clear the accumulator content. While perform this instruction, our accumulator will be 0 0. This is very useful instruction. For example, if you want to perform addition between a number of bytes, we should start with a clear by clearing the accumulator content. So it is applicable for what you say accumulator only, say R0 or R7 select or memory. Such instructions are not valid within our 8051 microcontroller. Next, this is also logical instruction. It's called rotate right. RR means rotate right and accumulator register. So accumulator register we can perform bit by bit rotation. Okay, so what will happen? Bit D0 exists from the LSB and enters into MSB D7. So 8 bits of the accumulator rotated right 1 bit. So what will be very clear? We have our accumulator. This bit is D0 and MSB bit is D7. D0 will move to D7. D7 will move to D6. D6 will move to D5. D5 will move to D4, etc. D1 will move to D0 will move to D7. That is what our rotate instruction will do. Let us see an example. Move A comma 36H. So A is equal to 0 0 1 1 0 1 1 0 36. That is what 3 6. This is corresponds to 3 and this is 6. While performing the first time RR instruction, RRA, what will happen? As we discussed, this is D0. It will move to D7. So 0 will come here. This 0 will shift here. This 0 shift to here. This 1 shift to here. This 1 will go here. 0 shift here. 1 will shift here. This 1 will shift here. So the content here, the latest updated while after the first instruction, RRA is 0 0 1 1 0 1 1. This corresponds to 1. This corresponds to 8, then 10, 11, 1B. So 36, 1B. So 1B, what is the number corresponding to 1B? 36 in hexadecimal system is 36 in hexadecimal system. 3 into 16. Let us see. 3 into 16 plus 6. That is 54. It is 54 in decimal, and 1B is 1 into 16 plus B. B is 11. So 16 plus 11 is 27. Okay, so 54 in decimal is changed to 27 in decimal after first rotation instruction. That means what happens here, the accumulator is now whatever the accumulator by 2. That is what RRA instruction is using. So we can perform a simple division by 2 by rotating the content of accumulator by 2. In hexadecimal also it is valid true. Just for understanding, I have explained to you in decimal system. So 1B is actually 36 by 2 in hexadecimal system, or 54 and 27 connected by 27 is equal to 54 by 2. So rotate instruction we can use it to just divide by 2. Next time again we are executing the RR instruction. What will happen? This 1 will comes to here. This 1 will comes here. Okay, can I show? This 1 will comes here. 0 shift here, shift here, shift here. Okay, this is what our result after the rotate instruction. Again here it may not be true whether it is divisible by 2. 27 by 2 1b by 2, it is 8. Then 4, no, it is not valid here. Anyway, then another one more time we are executing this instruction. This 1 will shift here, this 1, then very clear. Okay, then one more times we are executing the RR instruction. So this 0 will come here, 0, then 1 1 1 0 0 1 1. Okay, so just I want to show you some interesting result here. Before starting, our content was, at the first time our content was 36. After the last 4 times serially continuously we performed this rotate instruction, now the content is 63. So rotating the instruction, rotating the accumulator 4 times is just equivalent to swapping the lower order bits with the higher order bits. This 3 will shift here, 6 will shift here. So it will, continuously 4 times rotation is equal to swap of lower order bytes to higher order bytes. That is one of the application of rotate instruction, even though it is supporting what you called swap instruction also is supporting within the microcontroller, but we can implement it with what we called rotating the content 4 times to the right or left. We will see what it is. Then rotate left. Rotate left also rotating the content of the accumulator to the left. Before it was to the right and now it is to the left. So here it is reverse operation. D7 will go to D0, D0 will go to D1, D1 will move to D2, etc. D6 will move to D7. That is what our rotate left instruction. Example, A is equal to 72, then content 7 0 1 1 1 0 0 1 1 1. So what will happen? Rotate left RLA instruction, what it will do, this D7 will move to here. This 0 will move here, 1 to shift here, 0 shift here, 0 shift here, 1 here, 1 here, this one here. That is what our rotate instruction. Rotate left. Again once more, this 1 will shift here. Okay, then 0 here, 1 here. Okay, so D7 to D0 and D7 with the D6. That is what rotate left instruction. Now another rotate right through carry, RRC instruction, same rotation instruction, rotate right through carry. Perform the rotate right, but it is through the carry. So from the diagram it is very clear. D0 will go to the carry flag will go to D7. That is what rotate right through carry. So every time D0 is going to carry, so according to the bit D0, the carry flag will be modified. If D0 is 1, carry flag will be 1 after the rotate RRCA instruction. So we can check whether bit is D0 of a accumulator is 0 or 1. Okay, while performing RRCA, if carry set, jump on carry or jump on no carry, okay, that operations we can use to compare the particular bits of an accumulator. For example, if you want to compare D1 of the accumulator, whether it's 0 or 1, you can perform RRCA 2 times. Next time, after executing 2 times, if it is 1, indicates D1 is 1. So that is one of the application of RRC instruction. Okay, so let us see what with an example. Clear CY at the beginning, accumulator CY is equal to 0. At the beginning, CY is equal to 0. Okay, carry flag is 0. CLRC will make clear the carry flag. Move A comma 26 0 0 1 0 0 1 1 0 is the content of the accumulator. Then RRCA, what will happen? Carry flag was 0. So while performing the rotation instruction, the carry flag will be modified with the D0 content. So this D0 content will modify with our CY flag. So D0 shift here, then 1 shift here, this one here, 0 here, 0 1 0 0. Then how will be D7? Before in rotate right RR instruction, it was modified with the D0 value. That time here it is modified according to the carry flag. So carry flag is equal to 0 here. This 0 will comes here. This is carry flag. Again, next time when we execute RRC instruction, what will happen? This 1 will come to the carry flag. Okay, then 1 0 0 1 0 0 0. Again, this present carry will comes to this point. Another once more, if we execute the RRC instruction, this carry flag comes here. This is what our present carry. Then this one will go to the carry flag. Okay, so that is what our RRC instruction. So applications of these instructions are to check a particular bit. Second one, while actually our carry flag is holding particular bits, that bit we can send serially. So data serialization. Okay, this is carry flag, this carry content we can send it to. So first time what is here, this is D0, then this is D1, this is D2. So D0 can send it to a particular, say port P1.1, we can send it. Next time again So this time here it will be going 0. If you send now cy, it will be 1. Again, if you send d2, it will be 1. Like that, we can use the instruction to send a particular content parallel to serial conversion or data serialization. Okay, next RLCA, same operation and same application, but here instead here D0 is modified to D7 is modified to carry flag. D7 will be modified. Carry flag will be modified by D7, and the carry flag will come to D0. Whatever we discussed previously, it's opposite. So here rotate left through carry. Same applications and use also within the program. Now here write a program to find the number of ones in a given byte. So what the instruction is saying? Write a program that finds the number of ones in a given byte. Suppose we have a register with some value. Now here it is asking you to find how many ones are there in the given data. For example, we have an instruction move a comma hash 62h. So what is the content of a after this instruction? A is equal to 62. 62 is 0 1 1 0. 2 is 0 1 0 0 1 0. Now how many ones are there in 62? Answer is 3. So here you are it is asking to find how many. It means we need to count, we need to make the result is equal to 3. So to hold the result, let us initialize a register with 0. So move R0 comma hash 00h. So okay, so clear R0 register. Next, so we can keep our R0 here. Now how many ones are there? That is what we need to check. Let us do our rotation through RLC, rotate left through carry. So what is rotate left is doing? Rotate D7 will come to carry flag. So we will perform RLCA. What will happen? While performing this instruction, cy is equal to 0. D7 will come to carry flag. So D7 is 0 now. Now is carry flag is 0. So if it is 0, we don't want to count. So let us provide our count operation inc R0. Also we need to have how many times we need to rotate. So we should keep a counter here. That count we can keep in move R2 comma hash 08h. Okay, then we need to check whether we have checked all the 8 bits. So we need to increase the count also. Inc R2. Okay, so decrement and jump on non-zero R2 comma, where we should shift, we need to do the again once more rotation. So it is with a label again. So here is our again label. So if the content of R2 is non-zero value, it will, this is R2, it will make a rotation, it will make a jump to RLCA. Okay, now what time we need to do the count or content of R0 need to increase? If the after executing the RLCA, if the carry flag is 1, we need to increase, otherwise we need to skip. So here jump on no carry JNC to what next. So in that we will skip this operation. So next is we need to provide here same logic we used before also. So now the instruction, now the operation is completed. Let us see what will happen here. So our content of A is 62 and we cleared our R0 to hold the count the how many ones, and we have the count 8 times we need to do the rotation. Okay, first it will perform the RLCA. While performing RLCA, carry flag is equal to D7, and now D7 will be modified to D6. Anyway, whatever. Then jump on no carry. Yeah, it is now no carry. It will go to this. It will skip these instructions. INC. Sorry, it is not INC. It is decrement. DECR2. So decrement R2. So R2 is now 7, a non-zero value. It will rotate once more RLC. Once more RLC means now second time. So it is 7 now. That time our carry flag is D6. D6 is what? 1. So jump on no carry will fail. It will increase R0 to now R0 is equal to 1. From 0 0 to increase by 1, then decrease. So R2 will be 6 now. Again a non-zero value. It will jumps to here RLC. So carry flag is now D5. D5 is also 1. So jump on no carry will fail. Increase R0. So R0 will be 2. Again decrease R2. R2 become 5. Okay. Then a non-zero value, jump again, a rotate. So rotate make carry flag is equal to D4. What is D4? 0. So these operations will be bypassed or skipped. Then again decrease R2. So R2 is 4 now. Okay, a non-zero value, it will jump to again rotate. So carry flag will be D4. D4 is 0 now. It will not perform INCR2. Again decrease to 3. Decrease to 3 means it will check this value. Again decrease to 3. It will check this value. Once it is D1, what will happen? Again and 0 INCR0 makes and R0 to 3. So the R once R2 comes to 1 or 0, then if this condition will violate, it will go to another procedure, another step. So after the instruction, this instructions is repeated 8 times, our register R0 will be having the what you call the exact count of how many ones are there in the accumulator. That is one application. Now last instruction within the logical instructions, it is swap. It performs logical swap between lower nibble of accumulator register. In other words, the lower 4 bits are put into the higher 4 bits and the higher 4 bits are put into the lower 4 bits. Swap works only on the accumulator. So D7 D4 will come to D3 D4 place, D3 D0 place, and D3 D0 will comes to D7 D4. For example, A is equal to 27. Then if you perform swap A, now A will be 7 will comes to the higher order bytes and higher order will comes to lower order bytes. That is what our swap will do. Means equivalent to RR instruction performing 4 times. That is what our swap instructions will do within our 8051 microcontroller. With this I would like to conclude today's topic.